We live in a more connected age than ever before. Such technological shift has revolutionized how we communicate, but it has left our privacy more exposed to an increasing number of threats and violations. Privacy violations on social networks have been on the rise for many years and have become a critical concern for users. These violations can happen from different parties, including hackers, internet providers, and even the application service providers. Recently, there have been multiple data leaks linked with some big names in the social networking field, like Facebook Cambridge Analytica data scandal in 2018, in which the personal data of over 50 million Facebook users were leaked. Moreover, in 2019, there were over 1,400 data breaches, resulting in a whopping 165 million records being exposed in the US alone. Every 2 seconds, there is a new victim of identity theft. Despite that, 1/3 of internet users valued their online privacy at $100,000 to priceless. So why end-to-end encryption is not utilized in social networks? For many years, Alice and Bob have been relying on secure end-to-end encryption protocols for their communications. They have used various end-to-end encryption protocols, such as MT-Proto for Telegram, Signal for WhatsApp and Signal, iMessage protocol, Skype protocol, and many more. All these protocols have one thing in common. They were designed for relatively short-term sessions, meaning they do not require very long-term persistence nor the ability to be re-established. In addition, the focus is always on communication between two parties only. This has limited the development of end-to-end encryption protocols towards this ideology of short-term sessions between two parties. As a result, using end-to-end encryption in a social network was never practically feasible. Yet. Because in this video, you are going to learn about the STIC protocol, an end-to-end encryption protocol tailored for social network platforms. The STIC protocol is based on the Signal protocol, which is one of the most secure and widely used end-to-end encryption protocols. The STIC protocol was designed to be well suited for social network platforms, while preserving the state-of-the-art security features of messaging protocols. The STIC protocol is able to achieve this through what it calls sticky sessions. A sticky session is an end-to-end encrypted session between a user and a party that can be re-established after a state reset. That is when the user reinstalls the app or installs it on a new device, in an asynchronous and multi-device environment, and keeps track of the ratcheting message keys while preserving forward secrecy and introducing backward secrecy. Let's talk about the different key types a user would have. In the STIC protocol, Alice would have an identity key and a signed pre-key, both of which refreshes every while, in addition to a list of one-time pre-keys. Also, Alice would have a sender key for every party she is a member of. Alice can send Bob her sender key through a Signal pairwise session. Traditionally, Bob will not be able to decrypt Alice's sender key after state reset. In order for Bob to be able to decrypt the same sender key after state reset, Bob's private keys are backed up encrypted with a secret key derived from the password using Argon2, which is arguably the most secure hashing algorithm. Backing up the private keys encrypted will allow Bob to decrypt his own ciphered private keys after state reset, and therefore decrypt Alice's sender key. Nobody else, including the server, can decrypt Bob's private keys. But there is a small problem here. Signal pairwise sessions have perfect backward secrecy, meaning when Bob re-establishes a Signal session, he will be able to decrypt the first message or sender key only. To solve this problem, the STIC protocol allows two users to establish together multiple pairwise sessions. So every sender key will be encrypted using a dedicated pairwise session. This allows two users to re-establish all their sticky sessions after a state reset, while keeping the forward secrecy and backward secrecy of exchanging sender keys. Sticky sessions have a life cycle of n encryptions. After n encryptions, the session will go from an active state to a freeze state. This introduces backward secrecy every a maximum of n encryptions, and still keeps forward secrecy for every single encryption. In order to create a sticky session, Alice needs to contact the server to get the stick ID. In addition to the list of users that Alice needs to encrypt her sender key to, Alice can then check whether she already has a sticky session on her device associated with that stick ID and create one if needed. Then encrypt her sender key to the list of users individually using pairwise sessions. And finally, upload her encrypted sender keys to the server. Now let's see how Alice will be able to decrypt a photo X after state reset. First, Alice would verify her phone number. Upon verification, the server returns to Alice a limited access token, in addition to the initial password salt. Alice will use that salt to create the initial password hash, which is used in a technique called double hashing. This double hashing makes the user password never leave the device. The server will hash the initial password hash to create the double hashed password, verify it, then return to Alice her keys. Alice will decrypt her private keys with the help of Argon 2, then will re-establish pairwise sessions. Next, Alice will decrypt her own sender keys and re-establish her own sticky sessions. Now let's assume Alice will come across photo X, which she has not re-established its sticky session yet. Alice will fetch the sender key from the server associated with photo X, decrypt it, and re-establish the sticky session. Next, Alice will ratchet the chain the necessary number of steps to get the right message key. Decrypt the blob secret to get the blob key and hash, which she can finally use to decrypt and verify photo X. You can see that requests to the server that first needs verification are marked with a blue shield, while processing steps where there are decryption happening are marked with a golden key. You can see that for Alice to finally decrypt photo X after state reset, she had to go through 5 different decryption processes and pass 3 barriers. This emphasizes the security of the stick protocol. The end result of all of these security features is that Alice will have her posts end-to-end encrypted to the designated parties. Alice can view her posts after reinstalling the application. Alice can view her posts from any other phone. Alice still benefits from all of the security features of the Signal protocol, such as the extended triple diffie-Hellman key agreement. Sharing sender keys has perfect forward secrecy and perfect backward secrecy using multiple pairwise sessions. Sharing posts using sticky sessions provides perfect forward secrecy. And lastly, sharing posts using sticky sessions provides backward secrecy every a maximum of n encryptions, the trait which most group protocols lack. The stick protocol and its security features have been formally verified using VerifPal, a formal cryptographic verification tool in the symbolic model. The verification process has proved that the stick protocol provides useful security properties under a variety of adversarial compromise scenarios, such as many-to-many backward secrecy and self-healing in case of identity keys leakage. The stick protocol implementation is open source, available on GitHub. The stick protocol was implemented to be a fully comprehensive Android and iOS library, which can be simply dropped into a social network application, and provide end-to-end encryption using re-establishable sticky sessions with as low development overhead as possible. The implementation is composed of 4 software libraries for Android, iOS server and client handlers, covering the different development aspects end-to-end. The performance of the stick protocol's implementation has been evaluated, and the results show that using the stick protocol in a real-world social network application is feasible with negligible overhead. The stick protocol causes no noticeable compromise on usability or performance. In conclusion, this work was an end-to-end process of design and verification, to implementation and evaluation. We hope that the STIG protocol paves the way for more research into end-to-end encryption protocols for social network platforms.